Okay, hello. In the previous video, the main idea I wanted to show you was that the CDF can calculate any form of probability. So the CDF is defined as a probability smaller than something. But actually, if you know that probability, you can calculate probability greater than something or probability between 2 points. So any probability can be calculated from the CDF. But so this was an example, and we considered a numerical example from here. So from this three information, we can calculate probability in between 2 points, between these points, between these 2 points, right? If you do that, if you calculate probability between 11.9 and 12, and the probability between 12 and 12.2, what you're going to get is this result. So between 11.9 and 12, there is 25% probability, but 12 and 12.2 has 60%. The problem here is our numerical example was actually not consistent with the idea that the probability is a length. The probability does not need to be proportional to the length of the interval. This is an example. This interval has a length of 0.1, and this interval has a length of 0.2. So twice longer line contains more than twice larger probability, right? So it's not perfectly proportional to the length. So we have to expand our analogy, generalize the idea of length. So think about this. In the previous video, I explained you about the relationship between a point and a line. A line is composed of infinite number of points. Continuous points will make a line. So even one point has no length. A line has a length. So a point is zero dimension. There is no dimension for a point. A point is just one point. There is no size. It just has a location. That's it. But when you collect an infinite number of points, it will become one-dimensional line. Line is one dimension, right? So there is length. So that's how you measure the size of a line. Length is how you measure it. And now expand it. Generalize that idea. If you collect infinite number of lines, then you will have a square in two-dimensional space, right? So line, if you collect infinite number of lines, it will make a two-dimensional plane. I mean, a square, a plane, and its size is measured by the area. You can define area for any two-dimensional plane, right? A square, for example. And even more generalization will make it a cube, three-dimensional space. So if there is a plane, like say, think about paper. If you put an infinite number of papers, then it will become a book, which is a three-dimensional thick cube, like a box, right? Like box-like shape, three-dimensional object. Even though one paper is like two-dimensional plane, a book is like a three-dimensional object. And in 3 dimension, the size is measured by the volume. Volume is, how to calculate that. So this is how we expand and generalize the concept of dimension and its following its respective measures. So we are going to generalize our understanding from 1 dimension to 2 dimensions. So we are going to consider two-dimensional space to understand the probability. So that means, actually, in an earlier slide, I said the probability is a length. But actually, that's not always true. That's just for your understanding. That's just an introduction. Actually, but what's true is we are going to express the probability as an area. Area is sufficiently general to cover any probability, right? So we are going to describe the probability as a kind of area, as an area. So how do we do that? You have to make a two-dimensional graph so that you can calculate some area. Two-dimensional graph, like so earlier in one-dimensional graph, there is only one line. So this horizontal line was the one-dimensional graph. But now we add vertical line, which adds another dimension. So what we are going to do here is when you define an interval, for example, between 11.9 to 12, then earlier I told you to calculate the length, but actually that was not general enough. Now what you calculate is you calculate the area on top of that interval, on the interval below the curve, below this additional graph. So this is the area like this, right? So this colored area captures the probability. So you know the length, the width of the interval is 0.1 and the height of the curve is 2.5. So you know how to calculate the area of a rectangle. This rectangle's area is 0.1 width times height. So W times H. So it's 0.25, which is 25%. That's probability. This is the probability, and this is consistent with the information a numerical example that I gave you. And so from this graph, you can calculate any area. For example, the probability between 12 and 12.1 can be calculated by the area of this dark rectangle. Height is now 3, width is the same 0.1, so the result is 30%. So as you can see, even though this rectangle, this interval between 11.9 and 12 is as long as is of the same length as this interval, 12 and 12.1, still their probabilities are different because the height is different. Height is now 3, earlier it's 2.5. So if the probability is not proportional to the length of the interval, then it can be adjusted by drawing the graph according to the probability, proportional to the probability on that interval, right? So this is a very general way to describe the probability. A nice way to describe the probability, and also you can calculate any probability once you have this graph. Like for example, if you'd like to calculate the probability between 11.9 and 12.1, then just calculate the area here. You know how to calculate this area. Split the shape into two rectangles and calculate the area for each rectangle. So it's like 55%. So it's like elementary school, like calculating area exercise, right? So then the key here is in this approach, what you need is the graph. You have to have this step-like graph, or it can be smooth. Anyhow, you have to have a graph that allows you to calculate the area below that graph. We call that a probability density function, which is usually denoted as lowercase f and often called as PDF. And as I said, the purpose of this curve is to make the area under the curve as the probability, right? So, and of course, it is always non-negative. The probability cannot be negative, but what's tricky here is it doesn't need to be below 1. Even if the curve is greater than 1, the area can be smaller than 1, 100%. As you can see here, the probability density can be like greater than 100, like 1, even though the summation of the probability must be 1. So it's not exactly, it's just an aid, it's a tool to calculate the probability, but the curve itself is not a probability. And also what it tells you is that when the curve is high, that means the probability is more like higher on that interval. Like it's more likely in this area than this area, this interval. So the higher the curve, the more likely to happen. Like given if the interval was the same length, then higher curve indicates more probability. So this is just like an example, numerical example, to help you understand, to help you understand the idea. But of course, actual PDF, actual graph, it's not like this. The actual graph will be something like this, more smooth, and maybe you must be more familiar with this kind of graphs. Of course, this graph is just for like exercise, right? So for example, uniform distribution has this density, PDF, probability density, and it is called uniform because it's uniform in this interval. So this is the case where the probability is proportional to the length of the interval, right? So anywhere or any point is any interval is equally likely in here. And this is exponential distribution, as the probability goes down as the number increases. Usually exponential distribution is used to describe the distribution of lifetime or the longevity of a machine or equipment, something like that. And gamma distribution is also nicely shaped. It increases first and then goes down. It's a generalization of exponential. And today's main hero is the normal distribution, whose density looks like this. You know, this is the bell curve. The famous bell curve is the PDF, probability density, for the normal distribution, right? And the area, like area between 1 and 2, is captured by this area. I mean, the probability between 1 and 2 is calculated as the area of this shaded like part, shaded area. So it's rectangle, so easy to calculate, but the other guys is not a rectangle. Or the others are not rectangles, so we cannot calculate this area by hand. But of course, a computer can do it. Mathematically, we can do it. And at this point, I'd like to mention this. So I explained everything as if it's like elementary school level like math, but actually it's a very profound theory. So if you have learned integration from the calculus course, you may connect this idea to integration. Exactly, the area under a function is what integration does, calculates. So integration is to calculate the area on an interval below a function. So exactly, that's what you are going to learn if you like take more advanced statistics courses. Like, so for example, the probability between 1 and 2 is the orange area, which is integration of f between 1 and 2. And also, like probability between 3 and 4 is integration of the function f between 3 and 4. So, like, it's clear how you may apply the integration to a probability, calculating the probability using the probability density. But I'm not going to use integration at all in this course. You don't need to know how to calculate the integration. If you are advanced, if you are interested in further studies, then this is important point. But at least in this semester, you don't need to do any integration. So don't worry. Just I just want you to make sure I mention it. It's because it's so important for your further studies. Okay, summarize what we have done so far. First defined what is a continuous random variable. It is important, and the property of a continuous random variable. There are two properties I mentioned. Is that first, it has uncountably many outcomes, so we cannot list all the possible outcomes. And second, one outcome, a single outcome, has no probability. Single outcome has no probability. So as a result, our previous approach does not work. We cannot make probability distribution table for a continuous random variable. So it breaks down. We need a different approach to define and handle present probability distribution. And the alternative approaches, there are two alternative approaches I introduced in this chapter. One is the cumulative distribution function approach, CDF, and it's defined this way. The function is defined this way, and I showed you the function is defined as smaller than something, probability is smaller than something, but it could you can calculate probability greater than something or probability between 2 points using this information. So this is one thing. And the other approach you could use is the probability density function approach. It is using the function and integration. So you may understand it as so it is to calculate the area under a graph. So it's easier to understand, and it's easier to show as a graph where is the probability. So probability PDF would give you a nice graph like a bell curve, but the problem here is integration is not easy. So actually calculating area is not easy in many cases. So these two approaches have their own problems and merits, advantages, but I may use both of them from time to time. And the point is, we are going to use them. And in the next, so far, I did not start the normal distribution at all. So far was an introduction to continuous random variables. And from the next video, I'm going to start the normal distribution. But actually, from now on, so all the conceptual all the ideas, main ideas are introduced. So from now on, we are going to just apply those ideas to a specific example of the normal distribution. So it will be just some more numerical and more algebraic exercises from the next video. Okay, so see you in the next video. As I said, it's super important, so don't miss, and please watch it again if you are not confident you understood it. Okay, see you later.